go there, one thing to remember is that even though I'm only interested in those two equations from the third and fourth, I have 4 equations from Euler-Lagrange, I'm using the third, fourth. The actual form of equations is something like this. mz double dot equals p theta theta dot plus, I'm going to replace the Lagrange multipliers with forces. That way it is easier to understand. FC1 plus Jacobian FC2. So this is like the general equations which I wrote down. Here Z is going to be X double dot Y double dot theta 1 double dot theta 2 double dot. These are my constraint forces, and then those are the Jacobians. Okay, so that's the generic equation. I'll use these equations to derive the equations for footstrike. So equations for footstrike. Okay, so what's going on when I say footstrike is okay, remember that I've shown C1 to be my stance leg, and then C2 is the leg which is swinging. At foot strike, the C2 becomes the leg in front. It's the C1 is the trailing of the leg in the rear. It would then collide with the ground. Okay, so let's denote this case just like we denoted it for the bouncing ball as negative, just before collision. And then just after collision, we have I can just copy this. So I'll use plus for just after collision. Okay, so why the figures look same? What's going on? What's different? Well, what's different is the following, which is just before collision, what will happen is velocity of C1, okay, and I'll put a negative to indicate just before collision is going to be 0, right? Because that's the leg which was grounded. But after collision, C2 is going to be the new stance leg, which means that now velocity of C2 will be 0, but that's positive. So that's the difference. And that's like the key difference why you need to take that into account in my equations a little bit later. So the velocities of the contact points are going to be different, or the foots are going to be different. In one case, the trailing leg is going to have 0 velocity. In the other one, the leg in forward is going to have a 0 velocity. Okay, so with that, let's just go and see how to get the equations for foot strike. So we wrote down mz double dot equals p theta theta dot. That's the Coriolis force and gravity term. Then we have JC1 FC1 plus JC2. Okay, now what happens during collision? So I wrote the same equation, but what happening during collision is that the collision acts happens very, very quickly. It's like it's an impulse. It's not gradual. There's no spring. It's what we call hard collision. So those forces actually turned out to be impulses because it's not. It's sort of approximate that to be sort of like the bouncing ball, where velocity is downwards, and in a fraction of milliseconds, we don't model the velocities upwards for the ball. Similarly, here, what we need to do is, in order to account for that, we need to integrate these equations with respect to time to take into the effect of the collision. So these are integrated, and the integration time is the instant from just before collision to instant after collision. Okay, now we're going to sort of simplify these equations. The term which is on the right side, B, constitutes of gravity terms and Coriolis terms. Okay, now when we're doing that integration, we do integration of gravity and that Coriolis force with respect to dt. Since those, usually we assume that the forces due to impulses are so large that they have more significant effect than those due to gravity. So we can safely assume that even those forces are non-significant, the integral from t minus to t positive is going to be insignificant. So that integral is 0. Okay. The second, next we have two terms. Now, what are FC1 dt? It's basically, we can club that as the impulse. Let's call that impulse C1, and this is impulse C2, right? Impulse is the integral of force dt. Now, the first one gives me the impulse on the trailing leg, C1. The second one gives me impulse on the front leg. Now, we assume that the front leg, when it hits the ground, that is C2 hits the ground, there is a force, but the C1 is not really colliding against the floor. So the impulse on the trailing leg, the front leg has an impulse, the rear doesn't have an impulse because it's trailing. We can safely assume that C1, this term, is 0. So this is because gravity, Coriolis are small during impulse, or during foot strike. And this 0 is because trailing, no impulse on trailing foot, which is C1. So the only terms remain is the one on the right, and then this one, mz double dot. Okay, so what we'll do now is we'll integrate the equations. Okay, so when you integrate, we have the integral of z double dot, which is acceleration, is going to be z dot, which is velocity. And then we need to integrate this from positive to negative, or t positive. Okay, now why didn't I integrate m, right? M should also be integrated. Turns out that m, if you remember, m is only a function of angles, theta, and is not a function of velocity. During collisions, all the angles don't suddenly change. The velocity does change, like the bouncing ball, but the angles don't change. So I can assume that m, which is only a function of theta, is constant. So this m is a function of theta, and this is constant during collision. In other words, the angles won't change abruptly, though the velocity does. And that's why I can justify in taking m as a constant and then integrating only the acceleration. Okay, so this is equal to jc2. Again, jc2 is the derivative of the position with respect to q. It only has angles in it. I can assume that to be constant because the angles don't change. And I'm just going to take that fc2d2 as ic2. That's the impulse which I need to compute. Okay, so this can be written as mz dot plus minus mz dot minus equals jc2 transpose ic2. Let's call that 1. Okay, so this has 4 equations. Okay, the 4 equations are because of z is x, y, theta 1, theta 2. And so when you take the derivative of them, you will have 4 equations. But then there are 6 unknowns. Okay, why there are 6 unknowns? Where x dot, y dot, sorry, x, just write it this way, x dot, y dot, theta 1 dot, theta 2 dot, which is all z dot, is unknown. So all those 4 velocities after collision are unknown, but also this ic2, x, ic2, y are unknown. So there are 6 because of those 4 and those 2 due to impulses. So with 4 equations and 6 unknowns, you cannot solve for 6 unknowns because you don't have enough equations. It turns out there are 2 more equations which I have not accounted for. Those equations come because of the fact that velocity of C2 positive should be 0. So I'll write that down as an equation. Okay, I'm almost done. VC2 positive is JC2 positive Q dot equals 0. And those are 2 equations. Let me just make that number 2. These will be 2 equations. Okay, there are 2 equations because what is the velocity of C2? It's velocity in the x direction, velocity in the y direction. That's 2 equations. So what I end up is from 1 and 2, I can write this very compactly as M minus JC2 transpose JC2 0 Z dot positive IC2 equals MZ dot negative 0. So this is 6 equations, 6 unknowns. Okay. So we solve for Z dot positive and IC2. Okay, so those are the equations for foot strike. We want the velocities of all links after foot strike, and then we want the impulses. Actually, impulses we don't care about, but it turns out that we end up solving for it. Okay, so so we need to detect collision or contact. So in all my illustrations, the black leg was the trailing leg, and then the red leg is the one which is now made contact. So let's show that this is foot strike. So I'm going to write the angles. So we had, since the stance leg was the black leg, we have that angle to be theta 1. And then this angle to be theta 2. Okay, so let's just go and think of the figure first. I think these angles are incorrect. So θ1 is this angle, θ2 is that angle. So you can see that θ1 is positive counterclockwise. So this should be negative because I drew it clockwise. And then the other one, θ2 is correct. So when there's collision, one way to figure out collision is to compute the height of the foot which is going to collide, and then make that height go equal to 0. So that can be done in terms of cosines, but there's a simpler way of doing that. We know the length of the legs is the same. So if that's true, then and this line here, the dashed line is going to basically bisect that angle, make it into two. So we should have the fact that the two angles are equal. That is the angle on the, or minus θ1 should be equal to, or minus 2 θ1, right? So my bad. Minus 2 θ1 should be equal to θ2. So that means twice θ1 plus θ2 equals 0. And that's the condition I need to check. So when I do the integration in the single stance, I keep checking for the condition that 2 θ1 plus θ2 equals 0. And the moment 2 θ1 plus θ2 equals 0 is when the foot has made contact with the ground. Now, when you see that there's going to be one issue in this, which is that condition is also met when θ1 and θ2 equals 0. Right? 2 of 0 plus 0 is 0. And so what we need to do is when the legs are, when the legs are in that configuration, we need to ignore that because that corresponds to a condition which doesn't really correspond to collision. So there's a problem with this walker when you try to physically build it, which is when you have this walker on the flat ground, the foot will always stop against the ground, right? Because how else will it swing without colliding with the ground, because there is no knees in the model. So for humans, we don't stop against the ground because we bend our knees, and that bending of the knees prevents us from hitting the floor when we swing our leg. But that's not the case for this model. So we sort of have to ignore that condition, and we need to find when this condition is met, but when θ1 and θ2 is not close to 0. That will be taken care in my integration. Okay, just like the bouncing ball example, I don't know the time beforehand. I need to figure out when the height, in that case, ball example goes to 0. In this case, I do not know when the collision will take place, but by using the integration with this thing called events, I can figure out when to stop integrating. So that will come in the code. This is one thing, the only one thing left now before we do simulations is, if you look at the walker, it started 1, go to 2, 3, and 4, but from 4, we're back to 1, right? From 4, we need to go back to 1. Now, one way of doing this simulation is to keep track of the red leg as leg 1 and black leg as leg 2, and then you just simulate this. So it will be like you need to do 2 steps in order to have the walker repeat itself. That is, here the black leg is the stance leg, here the red leg is the stance leg. So next step, it will be single stance with the red leg being the stance leg, right? And so which means that I need to then create a simulation for 2 steps and then keep repeating that. Now that might be true for humans because our left leg and right leg are maybe having a different mass distribution in which I need to care about simulating 2 legs separately. But in this case, it seems like an overstretch to try to do 2 steps because the left and right of the front and back leg in here are the same. So what we do is, instead of trying to keep track of 2 steps, we just keep track of 1 step. And so what we do is we switch the legs. So the moment 4 occurs with the red leg is in front, we switch the red leg and black leg. So the black leg again becomes the stance leg and the red leg becomes the swing leg. And that way we don't have to do 2 steps, we just have to do 1 step. So we need to figure out what is the relation between what is that relation between the angles which will enable us to switch the legs? If we write that down, we'll so to simulate transition, we will switch the legs. Okay, and that will be clear when I draw this figure. So okay, so this is when, as I said, the red leg is always the swing leg. It has collided against the ground. And then this is the phase where we have theta1 positive, and this is theta2 positive. Okay, theta1 positive, by the way, is the same as theta1 negative. And theta2 positive, the same as theta2 negative. In other words, I'm saying is that before collision, after collision, there is no change in the angles. The angles are not changing because they are, you can't get a switch in the angles. However, the velocities will switch, and the velocity switch I actually showed here. The switch comes over here. So z dot, which is the rate of change of angle or velocity, is different from the velocity before collision, but not true for the angle. So this is the case of after collision. Let's draw the switch. This is just my convenience to make my life easy, to simulate one step, not two steps. So I'm switching the legs. So just swapping the legs. The black leg in now is the leg in front, and the red leg is a trailing leg because I switched. Okay, my convention is that this angle is positive and this angle is negative. Because it's clockwise. So what I need to do is I need to look at these two figures and then figure out how the angles are related. That is, I need to compute, my bad, this shouldn't be negative. I need to compute the value for theta1 and theta2 as a function of theta1 positive and theta2 positive. So just by looking at these figures, you can see that it's just, the easier one is theta2, right? Theta2 equals minus theta2 positive. Just look at this and this. And from there, you can see that the angles of the hip or the interleg angle should switch. Okay, the other one we can figure out by, let's see. So let's figure out this angle. Okay, so you can see that angle is theta2 positive, okay, which is in the direction shown. And then theta1, negative theta1 positive is clockwise. So what I'll do is I'll switch the direction of that. So it'll become minus of minus theta1. So it'll be theta1 positive. I did that because I want to switch this direction to be the other way, this way. And then I need to subtract that from theta2. So it'll be minus of this. So that is to make it consistent, I need to do that. So theta2 positive minus theta1 positive is that angle I've shown in green here. And then if you look at this, compare these two figures, let's compare this And this, you see that theta 1 this one is theta 2 positive minus theta 1 positive. No, my bad, this should be positive. Okay, why it should be positive is because of what I just said, which is this angle is positive theta 1 positive. Oh, then I'm something wrong. There's something wrong here because this should have been then negative. Just quickly check something. Yeah, I made some error somewhere. Let me figure it out. So what I get from my notes is this should be positive. But that is not consistent with what I have over here, this sign. So theta 2 positive is the angle. We draw this. This is theta 1. This is theta 2. And that's the convention, which is this is the stance leg, swing leg. Minus theta 1. Huh. Right, yeah. Yeah, so this, right, this should be, yeah, this should be theta 1 positive. And that's because the sign is already taken into account here, right? This should be negative. And so this will be negative, negative, it will be positive because it's this angle minus this angle. So it's positive and this sign is consistent. Thanks for that. Yeah, so you don't, what a mistake I did was I changed the sign and I also changed the direction of the arrow, which is not the correct thing to do. I need to either change the direction of the arrow, which means now it's already taken that into account, but don't change it twice because then it just means that I made a positive number go become a negative number. So these are the switching conditions. Switching angles. And then once I have that, I just proceed from, take that one step unit and keep integrating that.